Hello, class. We're going to just continue with the mole and molar mass lesson, and this next section is just specifically going to draw out some of the formulas that you're going to need. The previous video lesson, you may have seen me going through some examples of calculating a mass or a molar mass or maybe even a number of moles of something without a formula. And in that case, we're just kind of working through it using the concept of what is a mole. So at this point, we understand it's Avogadro's number of particles. It doesn't matter what we're considering. A mole applies in all cases to the same number of particles of that substance. We can mass compounds, and when we are considering a mole of the substance, then the mass that corresponds to that is called the molar mass. And these terms here, we're just going to give some formal symbols to. So in your package that you've received, you should have a couple of tables, and chemists, we work with calculations of mass to moles, or maybe vice versa, or we could be going from number of particles to moles. So we need to introduce some symbols here, some variable letters that allow us to work with these calculations in a formula or an equation. First one is little m. That's still mass, and you may have used that before in previous courses. For example, when you're doing density calculation, it's mass, little m divided by volume. So you've seen that variable letter before. It's going to be grams, and the symbol for the unit is lowercase g. For number of moles, we can't use little m and we can't use capital M, they're already taken. Capital M is the molar mass, so we use lowercase n. So that would be the number of moles as the unit, and the symbol is MOL, just without the E. The molar mass of the substance is in grams per mole, and we use the symbol G/MOL. Okay. So the formula that links these three quantities together. Let's first of all, before we write the formula, let's try to work out what the words are. Okay, so if we wanted to calculate a mass, that's probably the easiest one. If we wanted to know a mass, we would need to know how many units we have for our substance. That's how many moles, how many multiples, or maybe a fraction of a mole, and then how heavy it is. Okay, so the simplest way to approach this first one is that mass can be calculated using the number of moles, which is little n, and we multiply that by how heavy 1 mole is in grams per mole. That would be capital M. So that's the first formula. Little m equals n times big M. If we knew mass and the molar mass of a substance, and we wanted to determine how many moles we're working with, then we could take the mass, how heavy the substance is in grams, and we would divide by the mass of 1 mole. Okay, so in that case, mass divided by molar mass is equal to number of moles. The third type of calculation is not as common, because if we want to find the molar mass of a substance, of a compound, we would just look to the relative atomic masses on the periodic table. However, this suggests that there might be another way, empirically, of determining the molar mass of a new compound if the chemical formula was not known. But what we would need to know are two quantities. And in this case, the molar mass, because molar mass is in grams per mole, it's a ratio. So it's going to be another formula involving division. And in that case, because it's a ratio of mass to moles, and that pretty much from the units tells us which quantities need to be divided. We need to divide the mass by the number of moles. And that unit ratio in grams per 1 mole would be our molar mass. So the third formula is big M molar mass is equal to the mass divided by the number of moles. So these are formulas that can be used from the symbols, and if we work with them from the symbols, then the math is pretty easy. It's just multiplication or division. But we can also understand these from the descriptions too. And a third way of understanding them is from the units. And if we know the units, we may be able to find a quick way of getting the formula or the description, or at least the answer from given quantities. Now, let's pause at this point and let's look at maybe the use of a couple of these examples. You do have a worksheet in your handout package called Extra Practice Questions, worksheet 4.4a. In number 1, in determining the molar mass of each of the following substances, no formula is required here. This is just more practice calculating the molar mass for ionic compounds, and hydrate there in part D. Take note, okay, because this is a hydrate, you're going to have to include 6 water molecules in your molar mass, which means the molar mass of hydrogen multiplied by 12 and oxygen by 6, or you could find the molar mass of a water molecule and then multiply that by 6 and then add your cobalt atom and your 2 chlorine atoms. In number 2, let's look at an example here. Convert each of the following masses into an amount in moles. So we start out, we're in the lab, we measure out 8.40 grams. We look at the bottle, we know it's sodium hydroxide. All right, here's the formula that provides us with the number of moles. It's a ratio of the mass of the sample to how heavy 1 mole is. And that will give us the number of molar units, little n, for a compound. Now we need to know how heavy 1 unit is. Now this is not a molecule, this is an ionic compound. So 1 formula unit, which consists of a sodium ion and a hydroxide ion, has a certain molar mass. We calculate that from the relative atomic masses on the periodic table. Okay, and the values that I have drawn from might differ a little bit than what you see in your textbook, but 22.99, 16, and 1.01 give me exactly 40 grams per mole. Now, because we're looking at decimal places here, I'll carry 2 decimal places in my answer, and that's grams per mole. So that's how heavy 1 mole is. And then we can look at the 8.40 grams, and you should be able to say from that I have dispensed less than 1 mole. You should understand that much at this point, that if this is the molar mass, it's the mass of 1 mole, and this is the mass, that clearly we have less than 1 mole. Okay? Now we'll see that. It's going to be a ratio of the 8.40 grams to the 40 for 1 unit, and this will tell us that we only have a fraction of a mole. Okay, what fraction we have? Well, that's going to be 0.21. And I'm going to carry 1 more digit. Now, because my answer is exactly 0.21, I actually have to manufacture an extra digit here to match our precision in the mass with 3 significant digits. So I'm just going to add 1 more 0. That's a trailing 0. It's significant because the decimal point is present. Okay, so I'll continue to reinforce the rules for significant digits. But in this case, let's make sure we have proper units on that, and then that's equal to 0.210. So we have about a fifth of a mole of sodium hydroxide formula units. Now, number 2 is similar, except in part B, we have mass in kilograms. You have to have your mass in grams because your atomic masses on the periodic table are in grams for a mole of that element. So you have to make sure that your mass is always in grams, and that's keeping with what we have in our chart here, that the standard unit for mass is the gram. If we were to look at number 3, convert each of the following amounts into a mass in grams. So here we're working with the formula that says that how much we have is how many moles we have multiplied by how heavy 1 mole is. Okay, so in this case, we need still to know the molar mass of this compound. This is aluminum sulfate, so we're going to have to calculate the formula weight or formula unit mass for aluminum sulfate, and it has a lot of atoms in here. So we're looking at 2 times 26.98. We have in the sulfate group, we have a sulfur atom and 4 oxygen atoms. So if we have 3 sulfates, we would have 3 moles of sulfur atoms, each carrying 32.06 in mass, in grams per mole. We have actually in one formula unit of aluminum sulfate, we would have 12 oxygen atoms. So a mole of aluminum sulfate has 12 moles of oxygen. So multiplying that by the 16.00. So let's take those numbers and total up our molar mass for our formula unit. And I get 342.14. Okay, and I'm matching decimal places to my limiting values, which all are 2, and that is grams per mole. So I know that 1 mole has a mass of 342.14 grams, and we have almost a half a mole. So you can start to reason out that, well, we would have almost half of 342. So it's just a simple multiple. If we put our units in here, this time I'll show that with the units that it's helpful to see that the arithmetic actually works to give us our final answer, because we're wondering why would we multiply here? Well, we want to eliminate mole as a unit and produce grams as a unit. So we're going to multiply that by 0.456, and we're answering in grams. And the answer is, in this case, 156, and there's some decimal places, but since I'm holding 3 significant digits here with our limiting value, we have to report 3, so it'll be approximately 156 grams. Number 4 is, again, a little bit of the same, filling in the table from given information. And so what I would start with is go through the 4 rows and look at, okay, if I had to calculate the amount in moles, all of them you'll have to fill in this column. Okay, so this is required for each of those compounds. In each case, if you're provided with the mass, then you're calculating the number of moles. And so this would require number of moles equals the known mass times the calculated molar mass. This also would, mass times molar mass. And then if we're provided with a number of moles, we're trying to find a mass, that would have us calculating little m, which would be how many moles we have, and we would divide that by how heavy 1 mole is. Okay, so those would be the formulas that we're going to use in the parts for number 4. Notice in none of those cases are we actually calculating a molar mass from a formula. We're calculating it from the periodic table of the elements. Okay, so see the periodic table of the elements for those. Make sure you count the number of atoms correctly for all of your compounds. Again, just a reminder here that with the hydrate, you have to take the mass of 1 molecule of water and multiply it by 10 as one approach. And so at this point, here's the summary that you'll see in your textbook, the 3 formulas for moles, mass, and molar mass. Now there's a 4th formula which relates number of moles to number of particles. We know Avogadro's constant is, it's a symbol, but it's also a constant. So we're never having to calculate this. That's for the scientists to do, to come up with measurements of what that number is. But we could be calculating possibly how many particles, which is our number of entities, capital N, or we could be calculating number of moles, depending on what information we're provided. So let's go back to our table on the previous handout, and again, let's fill in some information here. So this is, for number of particles of a substance, it's capital N. The units, there are no units. It would just simply be atoms or ions or molecules, whatever the substance is. No particular units. If, again, we have lowercase n, we've seen that before, so that's number of moles. The unit has been introduced before as MOL. Avogadro's constant, again, this actually has no specific unit, but the closest one we can give is number of particles or entities, so sometimes that word is used, per mole. And so we could say it's really particles per mole would be the short form unit. Now, the formula that links these three quantities together is given. The really much explanation that are needed, I think, if we know how many particles are in 1 mole, that's Avogadro's constant, and we know how many moles we have, then the number of particles in total would just be multiplying those two together. So the variations of this formula, if you're wanting to solve for the number of moles, we divide both sides by the Avogadro's constant. So it would be how many particles we have divided by how many particles are in 1 mole would give us how many molar units we have. Okay, I'm just going to go back to this worksheet and just explain a couple more things. If you've got the hang of how to calculate the 4 different quantities based on the formulas that were summarized, you can go ahead and sign off right now. I'm just going to go through a little bit of an explanation about the solutions, and I just caution you, when you look at these solutions, you're going to see an answer, which is really important to take note of, and you'll see a calculation, but the calculation doesn't seem to match to a formula, and the symbols are not shown, the numbers and the units are shown. If you want a bit of an explanation about how this works, you can keep viewing the video. Otherwise, I'll see you in class tomorrow, and we can work on completing this as well as the questions from the textbook. Okay, I'm just going to show you this chart right here. It's a little bit intimidating at first when you look at it. We have the central quantity, which is the number of moles, and then from that we can link to any of the other quantities that we've looked at. So we have the mass of an element or the mass of a compound. We have the number of atoms or particles of an element, or we have the number of molecules or formula units. And you'll notice in each case, it's not so much a formula that links from N to any of the other symbols, but rather it's a rate. Okay, and in math class you may have done rate conversion, where you focus more on the units that you're working with, and you'll also see that in addition to the units, you always see multiplication. Okay, the operation that is used for rate conversion always uses multiplication. So when we're going back to this worksheet solution page, you will see multiplication in the first example, even though the formula, if you'd used the formula, you would have seen that number of moles is mass divided by molar mass. Another way of treating this type of question is to say, well, I have 8.40 grams, and I know that the ratio is that there's 1 mole for every 40 grams. So we did calculate the molar mass, and treating it as a multiplication, we would multiply by 1 over 40, which is the same as dividing by 40. So that gives us our answer there. If we were to look at the next question, here we're taking, again, a slightly larger mass, but again, we're multiplying by a rate, which is that there's 1 mole per 18.02 grams. Another thing you'll notice in this solution sheet here is that the answer is in kilomoles. So that's a just be cautious about how you use your prefix units. If you're going to work in kilo or milli amounts, your answer has to be matching that same prefix unit. Otherwise, I would suggest always convert to grams and always convert to moles per gram. However, in this case, the thing I want to point out is that you're multiplying by that rate. When you look at the questions in number 3, they'll look a little different again. Here in part A, we're looking at calculating mass, and mass has typically been introduced as how many units you have, how many molar units multiplied by the molar mass. This one's a little bit more straightforward. We see multiplication, but we also see the rate there in grams per 1 mole. And again, the nice thing about this method of rate conversion is that our units are always going to cancel out. So in the first one, grams cancels out, we're left with moles. In the questions number 3, moles cancels out, we're left with grams. So that idea of using a rate conversion all we need to know is what ratio connects the two quantities that we're working with. Once we know that ratio, it could be that there's Avogadro number of particles per 1 mole, or it could be that there's 1 mole for every Avogadro's number of particles. It could be that the ratio is that there's 1 mole for so many grams from the periodic table, or it could be that there's so many grams for every 1 mole. This ratio here can be used effectively with multiplication. If that method's not for you, that's fine. Focus on just working with the formula and rearranging it mathematically, and that's probably how I'll model all my solutions, but I find that the worksheets, for some reason, they seem to use this rate conversion method. So again, for those looking for a little bit extra practice, you can attempt, if you want some more challenge, some extra practice questions. This is just optional. Working with rate conversion as well. This can get pretty in-depth, where we can use 2 or more rates simultaneously to convert, for example, say a mass into a number of particles. And as long as we know those rates, we can apply them all by multiplication. In this optional worksheet, you're just trying to find number of atoms in 20 grams, or the number of grams for so many quadrillion atoms. In this question here, quadrillion is 10 to the exponent 15. Okay, so it's past trillion. In number 3, the mass of exactly 1 tablespoon of sugar. I think maybe it should read. Tablespoon is 15 milliliters, and we can assume that's approximately 15 grams if you want. And again, the number of water molecules for number 4, we can use the density equivalence that a mass gram of water is equal to 1 milliliter of water. So again, this is optional, and the answers are also provided in the PDF on the web. So I'll see you in class tomorrow.